So we'll talk about new estimates on the Hausdorff dimension of the Feigenbaum Julia set. And since most of the audience are familiar very well with notions in holomorphic dynamics, I will give only a very brief introduction, just recalling that if we have a polynomial, its field Julia set is a set of points which do not escape to infinity under iterates, and the Julia set is the boundary of the field Julia set, the set of points near which the dynamics is chaotic. And here is the picture of the Julia set about which I will eventually talk today. I will talk about estimates on the Hausdorff dimension of the Julia set of the Feigenbaum quadratic polynomial z squared minus c, where c is the famous Feigenbaum constant, approximately minus 1.4. So this polynomial is remarkable with the fact that it is infinitely normalizable, the first example of infinitely normalizable maps in real and complex dynamics. So let me briefly recall what is renormalization. When we want to talk about renormalization, it is more convenient instead of globally defined polynomials to consider locally defined maps, namely quadratic-like maps. And by definition, a quadratic-like map is just a ramified covering from one topological disk into a larger topological disk of degree 2. So basically here we mean that we have just one critical point and have a map of degree 2 in this definition. And we can, as usual, take the important is that if we have an open domain which does not contain the critical value, we can take its preimages and we'll have two preimages under our map. So this is what ramified means in this context. And just to remind, such a map called renormalizable with period p if we can find a smaller subdomain U prime, which under pth iterate of f will be mapped onto a strictly larger domain V prime as on the picture, so that the restriction to U prime of this iterate fp will be again a quadratic-like map. So again, we'll have only one critical point inside point of degree 2. And this restriction of fp to U prime is called a pre-renormalization of f. And if we take this pre-renormalization and appropriately rescale the domain, then the result will be called renormalization of f. So this is a brief reminder. So yeah, it doesn't matter this definition. Yes, yes. Mm-hmm. Mm-hmm. Yes, yes, it's. Mm-hmm. Yeah, I need this definition just to remind what is the Feigenbaum map, the periodic point. Mm-hmm. Yes, yes. Mm-hmm. So touching is allowed. And to remind that quadratic-like map is called infinitely normalizable if there exists a sequence of integers and j such that we have a sequence of successive renormalizations defined. So we can apply renormalization to the first map with some period in 1, then to the second map with some period in 2, and so on. And as I mentioned, so this Feigenbaum quadratic polynomial, it was the first example of infinitely normalizable maps discovered by Feigenbaum collaborators with relation to various important phenomena, such as the universality phenomena. and has stationary period of renormalization and I equal to 2 for each I. So this is just to briefly remind what is the Feigenbaum polynomial. And there are many interesting, remarkable results about this polynomial and other infinitely renormalizable maps. So most recently, for instance, Misha Lubich jointly with Dima Dudko showed that the Mandelbrot set is locally connected at the Feigenbaum parameter. But concerning the Hausdorff dimension, so the first result substantial about Hausdorff dimension of this Julia set was my joint work with Sutherland. We showed that it is strictly less than 2. Using some techniques developed by Avila and Lubich in their papers. Then I generalized the method to infinitely renormalizable quadratic maps with periodic combinatorics and real parameter C, and made some experiments. Suggestions that, in fact, for all real Feigenbaum maps, so infinitely renormalizable quadratic maps with periodic combinatorics, the Julia set has Hausdorff dimension less than 2. And now today I will report on the first estimate from below for the Feigenbaum Julia set, namely jointly with Igor and Warwick. We showed using rigorous computer estimates that this dimension is at least 1.4978. So this is one of the most recent results, but using more. Yes? Mm-hmm. Yes, yes. Yes. So the first theorem is based on a certain probabilistic scheme. So basically comparing estimates of what is the measure of points which under iterate go into a small neighborhood of the critical point, compare with the measure of point which escape the small neighborhood and never return. So there is some certain scheme to which we apply the numerics, and I generalize the scheme for other maps, for the class of maps, real quadratic maps with periodic combinatorics. Show that the same estimate holds, but I was not able to make rigorous computations. I made some computer estimates which suggest that it looks like they all have dimension less than 2, but I don't have a proof, a computer assisted proof of that fact. So today I will talk about estimate from below. So in fact, we construct a sequence delta n of lower bounds for the Hausdorff dimension of this Julia set. These lower bounds converge to this dimension. We know that they do, but we don't know how fast is this convergence, unfortunately. So we cannot obtain using the sequence as an estimate from above. If we know that the rate convergence, for instance, is exponential, something like alpha times gamma power n, then we could use this to obtain estimate from above. But for now, unfortunately, this is only estimate from below. And so Warwick Tucker wrote programs and estimated that delta 28, so one of the best you could obtain is n equal to 28, is bounded by this number. This gives this estimate. So to my best knowledge, this is the first estimate from below on the Hausdorff dimension of the Feigenbaum Julia set. Okay, so the estimates are based on the McMullen's eigenvalue method. So let me briefly explain what is it. So assume that we have a conformal dynamical system so collection of conformal maps from some domain in Rn to Rn. And assume that we have invariant density of dimension delta. This means precisely measure mu such that when we map some Borel set E injectively into some other set, then the measure of the image can be estimated as integral of the derivative raised to power delta. So this is what means density of dimension delta. This is something which also known is in holomorphic dynamics as conformal measures. Yes. We can assume that it's a probability measure, yes. Yeah, here it's assumed that mu is a finite measure. Assume that we have a finite expanding Markov partition, so meaning that image of each of the species of partition under the corresponding map will either be disjoint or contain any other piece Pj. And expanding means that basically the derivative of some iterate is strictly larger than 1. Now, having some partition, we can define refinement basically by taking preimages of this partition. So having a piece Pi of the partition and piece Pj, we can take Pj's preimage under Fi intersect with Pi, and what we obtain, if it is non-trivial, we would denote the piece of a new partition. And for the method, we also fix a sample point inside each of the species Pi, point xi. And the algorithm goes as follows. So if we have two pieces Pi and Pj, such that image of Pi intersect Pj non-trivially, then we can find a point y inside Pi, which is mapped to xj. So maybe just let me just write some simple-minded picture. So here we have some point xj inside piece Pj. We pull it back, and here we obtain point yij. And based on these new points, we can compute the transition matrix with entries Tij equal to derivative of Fi at this point Yij raised to power -1. And we set Tij if Fi of Pi does not intersect Pij, essentially. Now, based on this matrix Tij, we construct matrices T power delta. Here, T delta means we raise each of the entries of the matrix to power delta. So basically, the entries are derivatives raised to power minus delta. And we find delta such that the spectral radius equal to 1. So to recall, spectral radius of matrix is the maximal absolute value of the eigenvalues of this matrix. And these numbers alpha will be the estimates for the Hausdorff dimension, for the dimension delta of the measure. Namely, with the above conditions, if we have our initial partition P, we take its nth refinement, we take for this refinement delta, for which the spectral radius is equal to 1. So this will be our number alpha of Rnp, and these numbers will converge to the dimensions.
Probably there is, I don't understand, shouldn't it be t to the alpha or t to the alpha? And then you have...
Yes. Yeah, it will be more appropriate to write t to power alpha, you're right.
Yeah.
So here and here and here, this would be alpha. Okay, so this is Macmillan's method. Now he showed that for a hyperbolic polynomial, that is polynomial which is expanding on its Julia set, or equivalently polynomial whose critical points or all convergent to attracting periodic points. So for such a polynomial, there exists a unique invariant density of dimension equal exactly to the Hausdorff dimension of the Julia set. And thus, the previous algorithm allows to compute the Hausdorff dimension in this case. Moreover, Macmillan showed how to construct such a partition using external rays for a hyperbolic map. And so the eigenvalue algorithm applied to P computes the Hausdorff dimension of the Julia set. So this is briefly the Macmillan's algorithm. Yes, I will mention later also, but yes, well, I'll talk in more details about the Macmillan matrix. But basically, if we consider the spectral radius of the Macmillan matrix, then so the claim is that when n goes to infinity, it will be convergent to the exponent of the pressure function, which I will define later. And so Felix Pschitsky in ongoing work proves this for some larger class of maps, but I will explain later this fact for the Feigenbaum map. Yes. Yeah. Maybe I could. Yeah. So you probably cannot hear what is Felix saying, right? Can you? You can't. Okay. So for the future, I guess you can use. You need to turn it on.
I just commented that this limit is geometric pressure in this Hausdorff dimension. And in case this hyperbolic dimension in the general case, that is and coincides with geometric pressure. No, clean.
You can keep it noise. Okay, so here, for instance, an excerpt from the Macmillan's paper, where he discusses this method. He made computations for various hyperbolic Julia sets for C from -1 to 0.5. This is some results of the computations. And remark that, so I think Macmillan describes his partition of Julia set for hyperbolic maps, but in fact, for computations, it's easier to consider partitions of neighborhoods of the Julia set, and one can do it in various ways. One of the most easiest cases when we have real parameter C, say between -2 and 2, we can define the initial partition P just taking a sufficiently large disk around 0 and remove invariant neighborhood of the attracting cycle and cut by the real line. So say we have a period 3 attracting point. We take a disk, we remove invariant neighborhood, say some union of disks. And this will be our initial partition. So somewhere here we have the Julia set. This very crude picture. And then we take pre-images of this partition under iterates of our map, obtain refined partitions, construct based on them so this is a better picture. Construct based on them our Macmillan matrices and obtain estimates for the Hausdorff dimension. And here is just an illustration partitions for the map z square -1 for the this hyperbolic map. So this is level 2 partition when we take pre-images of the level 1, level 3. Now we have 8 pieces, 16 pieces, and so on. So here is more deep partition of level 12. So as you see, the pieces of partition converge very fast.
So you took external array of the fixed point.
No. I mean, it's coincidence because so here C is real. Therefore, you can say that your external array coincides with the real line. Therefore, it looks like, but in general, yes. So on this picture, we have period point of period 2 here, and I cut out some other small piece just for symmetricity, so that our picture had fourfold symmetry. It's not necessary, just for convenience. This is cut out another piece. Okay. So in his proof, Macmillan uses invariant densities. So we use instead Poincare series to study the Feigenbaum case. So let me briefly recall what is a Poincare series. Given a rational map f of z and a point z0 away from the postcritical set of f, the Poincare series theta of z0 delta is equal to the sum over all inverse iterates of this derivative raised to power minus delta. And Kirby distortion theorem implies that this does not, the convergence of this series does not depend on the choice of z0 as soon as it is away from the postcritical set. And so there exists unique delta critical, which does not depend on the node, such that the series converges for delta greater than delta critical and delta less than delta critical. So when delta so here not necessarily expanding.
It's critical. Only zero if it is not expanding, then the first zero, which is not about convergence like previous, but it's about exponential. Convergent direction, just as the zero says about fourth dimension, not about quadrant. Some situations like Feigenbaum, the side.
Yes, yes.
But you were interested in Hausdorff.
Yes, yes. Yes, but here I don't claim that this delta critical is always equal to the Hausdorff dimension. It's a separate notion of critical exponent of the Poincare series. So it's so exactly this. But this is not. Yeah. Yeah, yeah, it doesn't mean. No, it doesn't mean.
Okay, so you don't specify.
Yeah. Yes, I will specify in the moment. So.
Okay. More related to
Yes, so Macmillan showed, for instance, that if every critical point in the Julia set of rational map F is pre-periodic, then this critical exponent coincides with the Hausdorff dimension. But in fact, it is true for some other maps, for instance, for the.
It's a nice case.
Yeah, right. So to study the Hausdorff dimension of the Feigenbaum maps, we will compare the Poincare series with Macmillan matrices. So assume we have a rational map F such that Julia set does not contain infinity. Assume that it has a Markov partition as above, as was described above, of a neighborhood of the Julia set. And assume that we have chosen a point xi in each piece of the partition, as in the Macmillan's method. And we define modified Macmillan matrices by, instead of taking inverse derivative of inverse iterate at points xi, we will take the lowest possible value for this inverse derivative between two pieces pi and pj, namely so if we have our piece pi, we have f, here we have piece pj, so we find the point here inside pi mapped to pj, for which the derivative is maximal. Take inverse. This. Okay. So this will be our Macmillan matrix, new Macmillan matrix. Macmillan mentioned in his paper about the case of hyperbolic. Julia said that using these matrices, one can obtain estimates from below on the Hausdorff dimension. So we have matrix L I delta, ij of delta with these values. And in addition, we construct matrices of partial Poincare series. Namely, if we have two pieces Pi and Pj now, so that one of them is mapped under some large iterate, probably maybe large, maybe not, FL onto the other. So here, remember, we have marked points. And we denote by omega Lij the set of points zeta, which are inside Pi and mapped by FL to Xj, and introduce partial Poincare as sum of derivatives FL of zeta for such zeta raised to power minus delta. So this will be dependent on Li and J, and we construct matrices theta L of these values, theta Li J of delta. L, it's the length of the iterate. So we have map F, and for any integer L in this value, so we have sequence of matrices. So for now, we just define sequences of matrices.
Yes, but keep all the P,
For now, I assume that we have just fixed. It may be original P, it may be refined P. So for now, just any. Not really. It's a separate now. It's so here it can be any partition, but eventually we'll assume that it is some refinement. Yes. Mm-hmm. And proposition is that if we take Macmillan's matrix L composed with supremums of derivatives, raise it to power, what we obtain will be less or equal to the matrix of partial Poincare series theta L of delta. For every integer n. And just to briefly explain why this is just writing the definition. It's nothing special. This proposition, if we have a point zeta like this, mapped by xj, we can mark the indices I1, I2, and so on as they iterate. So we have Pi equal to Pi0. Then here we have Pi1, Pi2, and so on. So each time we obtain that F maps PIS on strictly larger domain than PIS plus 1. And so this by definition implies that the corresponding entry of the Macmillan's matrix is not equal to 0. And since it is constructed by taking maximum of the derivative on this domain, on the part of the domain mapped here, it is less or equal than derivative, in particular at point fs of zeta. So here, for instance, we have f of zeta. Now we denote by this nice written L of zeta delta, the product of all elements of the Macmillan matrix on this trajectory. And what you obtain that this product is less or equal than derivative of this iterate raised to power minus delta, just taking product of this inequality. And also notice that these entries, capital L of zeta delta, is exactly what appear when we take L's power of matrix L. And so summing the inequality which we obtained over all zeta from omega, we obtain exactly what we wanted, that the corresponding entry of the matrix L of delta raised to power L is less or equal than the corresponding entry of a matrix of partial Poincare series. But the idea is very simple, is that when we take L of delta and raise it to power L, we sum derivatives over pseudo orbits. So this product of LIS I plus 1 can be considered as derivative of pseudo orbit. And since it's taken with maximum possible values of the derivative, when we take minus delta power, we obtain less or equal than derivative of actual orbit. Now, as a corollary of the inequality between matrices, we obtain that if we have delta naught for which the spectral radius of Macmillan's matrix is equal to 1, then we have delta naught less or equal than the critical exponent. And this again is a simple fact. So let me briefly explain it. So to remind, if we have a square matrix A, its spectral radius can be computed as limit of norm of n's power of A raised to power 1 over n. If, moreover, the matrix A has no negative entries, and so that for some n, A power n has all positive entries, then by Perron-Frobenius theorem, the spectral radius can be computed as follows. We take any indices I and j, take matrix AN, its entry ij, take 1 over n's power. In the limit, we obtain exactly the spectral radius. So in the case of Macmillan's matrix, if we assume that the spectral radius for some delta is equal to 1, then we can show that for some I and j, ij's entry of L's power of the Macmillan matrix will not converge to 0. And due to inequality with the matrix of Poincare series, we obtain that the partial Poincare series theta Lij will be not convergent to 0. And so this implies that the complete Poincare series will be divergent. Yes. Mm-hmm. So the other condition is all entries of the nth power are positive. So there exists some power, so that when you raise power a to power n, matrix a to power n, all entries will be positive. So for the diagonal matrix, you have plenty of zeros, which will stay zeros. Mm-hmm. Yeah, this is true for our case because each piece.
Well, this is transitivity of matrix.
Yes, yes, right. Mm-hmm. Okay, so this shows that having a partition and taking Macmillan's matrix with maximal derivatives, we obtain an estimate from below on the critical value and on the Hausdorff dimension in the case of hyperbolic maps at least. And notice that for hyperbolic maps, one can simply define matrices based on infimum of derivatives. So instead of supremum of derivative from piece pi to pj, we can take infimum, take it power minus delta, and obtain similarly estimate from above. In the case of hyperbolic maps, as we saw, for instance, on the example of the picture for z square minus 1, the diameters of the tiles of refinements converge to 0 exponentially fast. And from this, it is not hard to show that difference between upper and lower Macmillan matrices converge exponentially fast to 0. And so the upper and lower bound converge. And this gives an alternative proof of Macmillan's eigenvalue method for the hyperbolic maps. So using Poincare series. So this was for hyperbolic maps. Now for Feigenbaum maps, we cannot define similarly a matrix U of delta by the obvious reason. We have 0 in the Julia set, and there will always be tiles which contain 0, maybe on the boundary, and so infimum of derivatives will be 0. We cannot raise to power minus delta, so we cannot construct the matrix in a similar way to obtain an estimate from above. Now let me explain what happens, what we do for Feigenbaum quadratic polynomials. So we define the initial partition in a very simple way, just by taking 2 half disks of radius 2, one in upper half plane, another in the lower half plane. So define the refinements which will be just connected components of preimages of this half disk under iterates of the Feigenbaum polynomial. So here is the picture. So partition of level 1 is just 2 half disks. When we take preimages under Feigenbaum polynomial, so we have 4 pieces, each of them containing 0 on the boundary. Then 8 pieces, 16, and so on. This is example of more refined partition of level 12. Next, so we define this McMullen matrices. Ln of delta, n is index for the level of partition, and define delta n as supreme of delta for which the spectral radius is less or equal to 1. Then by corollary, which we just saw, this delta n will be a lower bound for the critical exponent for the Feigenbaum polynomial. But Avila and Lubitsch showed that in the case of the Feigenbaum map with zero area Julia set, the critical exponent also coincides with the Hausdorff dimension of the Julia set. So again, this will be equal in this case to the Hausdorff dimension of the Feigenbaum Julia set. And these are it's not normalization, it's refinement. So as before, we just take pre-images of the pieces, obtain smaller pieces. So Rn is refinement of the Markov partition.
You don't say about renormalization.
No, here so far I don't did. We have a sequence of refinements. Yes, we have sequence of estimates delta n, and so using Igors computer estimates, using a program designed by Warwick tracker, we obtain this bound 1.48978.
But this doesn't see normalization.
Not yet. Yes.
Okay.
Yes, yes. For this, you don't really need normalization to obtain the lower bound. Yes, so what you need, you just need to know that you have some Markov partition which will converge in diameter to 0 when you take pre-images to obtain nice estimates. They do shrink to 0, but not exponentially fast.
What does it mean refinement? I just meant refinement as taking pre-images.
Yes, pre-images.
Then you have no way to see the shrinking of puzzle pieces are all to the level.
So they do, but so let me see what it means.
Because if you take piece after the normalization, all they follow the same pattern. They don't distinguish because this after the normalization.
So we take connected components of the pre-images. And because we cut initially using the real line, when you take pre-images eventually, so maybe you don't need to think about the pieces where normalization is defined. It's different kind of pieces. Yeah, that's the problem. Yes, so I think. Yes.
in the middle because neighborhood of critical points sits deeper and deeper. But if you start different value, okay. Makes sense.
Okay, so let me continue. So this is some of the graphs of the spectral radius of Macmillan's matrices, Ln. So this is constructed by Warwick. So another illustration, the values of delta n. So these approximations, this bounds from below for the Hausdorff dimension. So there are two colors. You can see here blue and red for even and odd levels. And Warwick noticed interesting fluctuations here that if we take difference between two consecutive bounds, so you see this difference below, it's difference multiplied by 5. And it fluctuates getting larger and smaller every 2 steps. Just an observation. And in the limit, I think Warwick mentioned that it looks like this sequence approaches value of like 1.53 or something like that. Okay. Now, so another piece of the story related to this work is what I mentioned before, tree pressure, which can be used to show that our estimates delta n from below actually converge to the true Hausdorff dimension of the Julia set. So what is tree pressure? Given a rational function f and point y, away from the postcritical set of f, we can consider some of derivatives of L's iterate over all preimages of y under FL, raise it to power minus delta, take logarithm, divide by 1 over L, and consider the limb sup. So there's one of several pressures, particularly defined by Felix Chuditsky and studied extensively with co-authors. Notice that by Kirby distortion theorem, this value does not depend on the choice of y if we choose it away from the postcritical set.
In fact, one can choose anything not too fast approximated. Here the polynomials we can take from just outside.
So yes, for polynomial. Okay. So proposition, the spectral radius of Macmillan matrices converge to the exponent of the tree pressure for the. So we prove it for Feigenbaum for periodic points of normalization for real quadratic maps with periodic combinatorics, in particular for the Feigenbaum quadratic map. But as I mentioned in ongoing work, Felix Chuditsky proves a similar statement for a larger class of large class of maps. You can use your microphone for comments because I guess online participants can't hear you. So now let me just give you a hint on the proof of this convergence in the case of the Feigenbaum quadratic map. So just to recall, delta n is the supremum of delta for which the spectral radius of the Macmillan's matrix Ln of delta is less or equal to 1. And the corollary which we obtain is that delta n converges to the Hausdorff dimension of the Feigenbaum Julia set. Now, yeah, they coincide. Mhm. But since we wanted to obtain the value of the Hausdorff dimension, we are happy that we have this, that it converges to the Hausdorff dimension, so we can at least guess what will be limit by studying this sequence. Okay. Now to compare the spectral radius of the Macmillan matrix with the tree pressure. Once again, so assume we have a point zeta as here, mapped by some iterator L to xj, and let E0, E1, E2, and so on be the sequence of indices of p's which the orbit of zeta visits. And we have the product of elements of the Macmillan matrix over this orbit. And to show that limit on the spectral radius of ln of delta is equal to exponent of the tree pressure, the key lemma is the following: that the product of the entries of the Macmillan matrix divided by the derivative of the true iterate. So Macmillan's matrix gives us product of entries of Macmillan matrix gives us kind of derivative of pseudo orbit, but also we have the true orbit. So the ratio is bounded by some gamma n raised to power L, where gamma n converges to 1 when n goes to infinity. And a very quick idea of the proof is that, so we have here 0, we have some pieces containing 0. And if we consider an orbit of a point under the Feigenbaum quadratic polynomial, it can visit pieces containing 0 some number of times, but this number of times can be explicitly bounded by how far we started from the origin initially. So basically, if the distance from a zeta, from an initial point zeta to 0 is of order constant to power n, then it will require us, due to renormalization property, iterate of length to power n to come back on the same distance. And this allows us to control product of ratio of derivatives on each step of our iterate. This very brief idea. And this basically finishes my talk, finishes what I wanted to tell. It finishes the proof of convergence of our lower estimates to the Hausdorff dimension of the Feigenbaum Julia set. That's it. I guess I finished very earlier. Okay, thank you very much.
Questions? Online. No questions? Do you hear me? Nice picture.
You mean from the previous papers? Yes, it was not very relevant. So. Yes. Yes, for the tree pressure, that's true. So just to explain so the picture which we have. So this is our spectral radius of Ln of delta. Here we have Ln plus 1, Ln plus 2, and so on. In the limit, we have the graph of exponent. Yes. So in the case of the Feigenbaum quadratic polynomial or other periodic points of formalization, we have this picture. It's easy to see. Yes, I guess you're right. In general. But this actually, yes, Warwick Tucker, so based on our algorithm, wrote a program for making Igors computer estimates for these graphs and computing the points of intersection and obtained. Yes. Yes, right. Okay.
So to you and maybe also to Warwick, I mean, what if you do a sort of Richardson extrapolation or something like that on these delta n's? What happens? Warwick said something about that he sort of extrapolated it was 28, but maybe it's best to have powers of 2 or something. Do you have some comments? What do you expect if you let n go to infinity? Do you expect something?
Yes, so Warwick said that It looks like the limit can be something of 1.53, something approximately.
Yeah.
I think he used, I don't remember what he said, exponential.
Yeah, that's probably what's sometimes called Richardson interpolation, extrapolation.
Yeah.
But I don't know if this is valid. It sort of assumes some analyticity in the parameters.
Yes,
this is something that seems to work, but one doesn't know why it works. In less complicated cases than this also.
Sorry?
Even in less complicated cases than this.
Yes, for hyperbolic, so it is known that convergence is exponential.
Yeah.
For hyperbolic, it's
then it should be valid. It should be valid. This.
Yes, right. So for now, we don't know. We have some ideas on how to develop a scheme for estimating this dimension from above, but it seems much more complicated question. So the best, what we can say now is that it is less than 2.
Yeah.
Okay. Thank you. Thank you, everyone. So we don't have a speaker for next week, right?
Maybe we stop